Welcome. Today we shall go on a journey right to the center of a neutron star. But first, let us recall how nature makes neutron stars. In stars more massive than roughly 10 times the mass of the Sun, the stellar nuclear drama, which consists of many acts, proceeds all the way till the final curtain comes down, till silicon fuses to form iron 56 nuclei, which is the most stable nucleus. Till that stage, matter remains classical and non-degenerate, and the safety valve, which I have explained several times, remains in operation throughout this many acts of this drama. This is because till that stage, till silicon fuses to iron, the radiation pressure always remains more than 9.2% of the total pressure, and according to Chandrasekhar's rigorous theorem of 1932, matter will remain classical if this condition is satisfied, regardless of how high the density may become. Till that stage, cooling is mainly due to photons, which is extremely inefficient, which is why radiation pressure remains more than 9.2% of the total pressure. When the iron core begins to form, if you were to look at the very center of a massive star, you will find the core, which will be roughly 1,000 kilometers in radius, looks like an onion. It has many layers. Iron, silicon, oxygen, neon, carbon, helium, hydrogen, and there is burning, still fusion going on at the boundaries as indicated in this onion skin model of a massive star. Now, when silicon fuses to form an iron core, silicon will fuse at a temperature of 10 to the power 10 Kelvin, suddenly the neutrino luminosity will become much greater than the photon luminosity. And the neutrinos escape instantly, unlike photons which have to struggle and diffuse their way out. Therefore, because of the enormous neutrino luminosity, the radiation pressure finally drops below 9.2% of the total pressure, which is the sum of gas pressure and radiation pressure, and the iron core now becomes degenerate. It now obeys Fermi-Dirac statistics. So, an iron white dwarf forms at the center of a massive star. Within a few hours, 8 or 10 hours, remember this stellar drama has been going on for about 10 million years, but the final act will only last a couple of few hours, 8 or 10 hours. The mass of the iron core grows because more and more silicon fuses to form iron, and eventually the iron core grows to the mass of 1.4 times the mass of the Sun, which is the Chandrasekhar limiting mass for a degenerate star supported by electron degeneracy pressure. And a dynamical collapse occurs on a time scale of a millisecond. The end result of this dynamical collapse of this core, iron core, is the formation of a neutron star. That's explained in this figure, which I have shown you before. Here you have an ordinary star consisting of electrons, protons, and neutrons. The core collapses and it forms a neutron star whose radius is roughly 10 kilometers and its density is about 10 to the power 14 grams per cubic centimeter. When the core collapses from 1,000 kilometer radius to 10 kilometer radius, an enormous amount of gravitational binding energy is released. Gm squared divided by R, this is the initial gravitational binding energy, this is the final gravitational binding energy, and the binding energy release is of the order of 0.1 times the rest mass energy of the star, and then the star simply blows up. This is the scenario of core collapse supernova. The core collapses, forms a neutron star, the gravitational binding energy results in a supernova explosion. Now I want to discuss supernova as the ground state of matter. Matter can be regarded as in the absolute ground state if it is at the absolute zero of temperature or at extremely low temperature. But first, let me make this remark. The collapse of the iron core to form a neutron star is so rapid that one can safely assume that strong, weak, and electromagnetic forces will adjust the nuclear composition to the thermodynamically most favorable one, namely the one with the lowest free energy. Now let's proceed. The neutron star will be born incredibly hot, and it will quickly cool to a temperature of about 1 billion degrees. Now you will be very surprised at my calling an object at 10 to the power 9 Kelvin a cool object or a very cold object. I'm entitled to do that for the neutron star for the following reason. Hot or cold, small or big, doesn't have any meaning in physics, as I have stressed many times. You must compare it with something. So matter can be regarded as cold if it can continue to remain in the ground state. In other words, the temperature of the body is not enough to excite it to the various excited levels, whatever those excited levels may be. In this case, we are considering energy levels inside the nucleus. The energy levels inside the nuclei are separated roughly by several millions of electron volts. How do I know that? Because when it jumps from one level to another, it emits gamma rays, and gamma rays have energies of the order of 1 million electron volt, MeV, capital MeV. Now I've already said that 1 eV is roughly 10 to the power 4 Kelvin. Therefore, several MeVs will correspond to a temperature of several times 10 to the power 10 Kelvin or closer to 10 to the power 11 Kelvin. Therefore, compared to the typical excitation energies, which are of the order of 10 to the power 11 Kelvin, a star at a temperature of 10 to the power 9 Kelvin is an extremely cold object. Thus, I can safely regard the matter of the neutron star as being in the lowest possible energy state, namely the ground state of matter. And now let us ask the following question. What is the ground state of matter at zero pressure? Well, I have a collection of neutrons and protons and electrons. The total number of electrons is equal to the total number of protons, so it is electrically neutral. What is the lowest energy configuration of this matter? Well, let us try to systematically reduce the energy of each degree of freedom. First of all, I have lots of neutrons and protons. If I bundle them into little nuclei, iron 56 nuclei, then that will have the minimum energy because it has the maximum binding energy per nucleon. So I shall do that. Instead of letting all the neutrons and protons be in the bucket, I will pack them into iron 56 nuclei. Now, if the nuclei are moving around like in a gas or a liquid, there is a lot of entropy and kinetic energy. I'm going to reduce that to a minimum by arranging the nuclei in a perfect lattice to minimize the configurational energy. Now you can worry about what should be the crystal structure. Is it going to be a simple cubic lattice, or a body-centered cubic lattice, or a face-centered cubic lattice? Then a good solid-state physicist will tell you which will be the lowest energy lattice configuration, and we will put the iron 56 nuclei into that lattice configuration. Now the electrons have a lot of entropy. There are spins which are oriented in random directions. So it is a paramagnet. I can reduce that energy and entropy by aligning all the electronic spins so that the iron becomes a ferromagnet. Now, I can also argue that the outer 1 kilometer of the star will be a solid crust. Why is that? I can calculate what should be the melting temperature of the solid at that pressure. And as long as the temperature of the star is well below the estimated melting temperature, I am safe in assuming that the outer layer, roughly 1 kilometer out of the 10 kilometers, will be a solid crust. Therefore, I am ready to make the first consequential statement. Namely, the outer crust, roughly 1 kilometer in thickness, will be a ferromagnetic iron 56 lattice, because this is the lowest energy configuration. Now, the stability of the pulses from a pulsar tells us that the magnetic field is anchored to the surface of the star. Now, if the surface of the star was a liquid or gaseous, then this magnetic field will not be anchored and the pulses will not be stable, one pulse after another. And that tells me that the magnetic field is anchored to a solid crust. So observationally, I have good evidence to support my conjecture that the outer 1 kilometer of the star will be a solid crust. Now, let us proceed inwards. As one gets deeper, the density will increase dramatically due to the gravitational pressure. The pressure is just the weight of a unit cylinder sitting on top of my head as I go down from the surface into the interior of the neutron star. And if you do a simple estimate, you can convince yourself, if you go just a few millimeters below the surface, you will already reach a pressure far exceeding the pressure at the center of the Earth. So please make an estimate of what will be the depth inside a neutron star where the pressure will equal the pressure at the center of the Earth. By the time one reaches 10 to the power 4 grams per cubic centimeter, the atoms will be completely ionized because you're squeezing the atoms together and the outer electrons will all pop out and you will have ionized atoms. As you go further down, at a density of 10 to the power 7 grams per cubic centimeter, 10 million grams per cubic centimeter, the free electron gas will not only be degenerate, it will be relativistic. Remember, the free electron gas is degenerate even in sodium or copper. So there is no question of electrons and neutron star surface not being degenerate. What I am saying is by the time you reach a density of 10 to the power 7 grams per cubic centimeter, the electrons will be relativistic, moving at speeds comparable to the speed of light. Around this density of 10 to the 7 grams per cubic centimeter, the Fermi energy of the electron will exceed 1 million electron volt. Fermi energy is the highest energy level up to which all states are occupied with 2 electrons with antiparallel spin and above which all states are empty. And this Fermi energy in a metal like sodium or copper is a few electron volts. Here, the Fermi energy, it will be a million electron volt. Remember, the Fermi energy EF increases as density to the power 2 by 3. Now, when you reach that density and when the Fermi energy reaches a million electron volt, iron 56 will no longer be the most stable and the most favored nucleus, because At that density, iron 56 nucleus will become unstable to inverse beta decay. What is inverse beta decay? Beta decay is when the neutron decays to a proton and an electron and an antineutrino. Inverse beta decay is when the proton combines with an electron at the top of the Fermi level and transforms itself into a neutron and a neutrino, and of course the neutrino will escape. So this is inverse beta decay. So neutrons inside iron 56 nuclei will get converted to protons. Therefore, iron 56 will no longer be the most stable nucleus. So the electrons on top of the Fermi sea will combine with the protons to form neutrons, and the neutrinos will escape. Nickel 62 will now be the most favored nucleus, and as you go a little further down, nickel 64 will be the most stable nucleus. These nuclei differ from iron 56 in that the number of protons in the nuclei have increased because the neutrons have been converted to protons. Sorry, the protons have been converted to neutrons. Excuse me, I made an error there. The protons have combined with electrons to form neutrons, and therefore these nuclei, nickel 62 and nickel 64, are much more neutron-rich than iron 56. Therefore, they are also much more unstable than iron 56. Thus, through inverse beta decay, the nuclei will become more and more neutron-rich. As we go down to the density, as the density increases, and when the density increases to this magical value, which is 4.3 times 10 to the power 11 grams per cubic centimeter, we will encounter an exotic zoo of nuclei. We will encounter, first, we had iron 56, that became nickel 62 and nickel 64, because the electrons at the top of Fermi level combine with protons to form neutrons. If you go further down, you'll get selenium 84, germanium 82, zinc 80, and so on. If you go further down, you'll get molybdenum 124, strontium 120, and krypton 118. Superman's planet was Krypton, if you remember. Now, these are not nuclei we find on Earth. These are incredibly neutron-rich nuclei that exists only by virtue of this enormous pressure that obtains as you go down from the surface of a neutron star. Now, there is something very special about these nuclei if you have studied some nuclear physics, those of you who are studying MSc physics. The second row of nuclei have 50 neutrons. The third row of nuclei have 82 neutrons. You will recognize that these are closed shell nuclei. Just as you have closed shell atoms, you have closed shell nuclei, and these are more stable than open shell nuclei. So let us summarize what we have said so far. The outer 1 kilometer is solid. It is crystalline. It consists of iron 56 lattice, which is in a ferromagnetic state. We are talking about a neutron star whose mass is 1.4 times the mass of the Sun. Radius is roughly 11 kilometers. For that model, the crust is about 1 kilometer in thickness. Now, let us go further down and let the density increase beyond 4.3 times 10 to the power 11 grams per cubic centimeter. As the density increases, the nuclei become so neutron-rich. Why are the nuclei becoming neutron-rich? Because protons are getting converted to neutrons by combining with electrons from the top of the Fermi level. The nuclei become so neutron-rich that the nucleus is not able to hold that many neutrons. So neutrons come out of the nuclei. They drip out of the nucleus. Therefore, what we will have is a lattice of exotic nuclei, so they're shown here, embedded in a sea of neutrons. This is very reminiscent of metals on Earth. What we have on Earth is when you bring atoms close together in metals, the outermost electrons, the valence electrons, pop out of individual nuclei and they become property of the entire solid. So you have an electron gas which is degenerate, which is what is responsible for phenomena like superconductivity, magnetism, electrical conductivity, thermal conductivity, or what have you. Now what we're saying is, when you bring the nuclei closer and closer together, and when the nuclei become more and more neutron rich, the neutrons spill out of the nucleus and form a free neutron gas. So let me show this pictorially. One picture is worth 10,000 words. Originally, we had a lattice of exotic nuclei. Now, what we are saying is that more and more neutrons are dripping out of the nucleus, and so we will have a neutron fluid. So as a result, what we will have is a crystalline solid which consists of exotic nuclei and a sea of neutrons. Remember, there is also a sea of electrons that has been there right from the surface, and these electrons are relativistic and highly degenerate. But we are not concerned with electrons now. We are only talking about the neutrons. So as you come down, you will have a lattice, but now you will also have a sea of neutrons. Let's see this pictorially. So what I have said so far is the following. The outer 1 kilometer is a solid crust with a relativistic electron gas. The lattice is iron 56 ferromagnetic lattice. As you go further in, beyond a greater than a density of 4.3 times 10 to the power 11 grams per cubic centimeter, matter gets neutronized so much that neutrons pop out of the nucleus, and you will have a Fermi liquid of free neutrons. That is what I've indicated by this blue shading over there. So you have therefore the lower part of the crust consists of a solid with a relativistic gas of neutrons and a degenerate gas of relativistic gas of electrons, and a degenerate gas of neutrons which have dripped out of the nucleus. And then finally we come to a density of 2.5 times 10 to the power 14 grams per cubic centimeter. That's a magical number because that is the density of atomic nuclei on Earth. So if you go through the periodic table, if you divide the mass of the nucleus by the volume for all the elements, you will get a density of roughly 2.5 times 10 to the power 14 grams per cubic centimeter. That is the matter of which we are made of. So we will reach the density. What is the significance of the density? At the density, you're squeezing the nuclei so close to one another, the distinction between individual nuclei is lost, and then you will simply have a sea of neutrons and a sea of protons. And of course, electrons have always been there. Therefore, right at the center, you will expect just a fluid of neutrons and protons. How many neutrons will be there? How many protons will be there? Or rather, what fraction will be neutrons? What fraction will be protons? And what fraction will be electrons? That is decided by the principle of beta equilibrium. Now, this is a very important principle for you to understand well. So, above a density of 2.5 times 10 to the power 14 grams per cubic centimeter, the nuclei will melt. In other words, the nuclei will lose their identity, and one will have a fluid of neutrons, protons, and electrons. the relative number of neutrons, protons, and electrons can be obtained by demanding equilibrium under beta decay. What does that mean? It means that neutrons will be decaying to protons, electrons, and antineutrino. Inverse beta decay will also be happening in the opposite direction. Protons will combine with electrons to form neutrons and neutrinos. These two reactions must balance one another. That is known as chemical equilibrium. And for that chemical equilibrium, what you need is that the chemical potentials or the Fermi energy of the neutrons must be equal to the Fermi energy of the protons plus the Fermi energy of the electrons. So that's what I've written here. So for this beta equilibrium, for this reaction to go equally in both directions, for there to be chemical equilibrium, there has to be beta equilibrium, which means that the Fermi energy of the neutron must be equal to the Fermi energy of the protons plus the Fermi energy of the electrons. Now, if you impose this condition, you will find it's a very simple calculation, and I urge you to do this calculation. You will find that roughly 95% will be neutrons, roughly 5% will be protons, and of course there have to be an equal number of electrons for charge neutrality. So what we have is the following. You have the outer crust of iron 56 ferromagnetic lattice. You have the inner crust above a density of 4.3 times 10 to the power 14 grams per cubic centimeter. You will have a lattice of neutron-rich exotic nuclei immersed in a neutron fluid which has spilt out or dripped out of the nucleus. If you go further in, beyond the density, which is the nuclear density, you will have a liquid core which consists of neutrons and protons, and beta equilibrium tells us that 95% will be neutrons and 5% will be protons with an equal number of electrons. Number of electrons should be equal to the number of protons for charge neutrality. Then if you go right to the center, where the density is 10 times, several times the nuclear density, then it's an open question. We just don't know what you will find at the center. Now, how do we know all this is true? Is this all hand waving? No, this is all from good physics. There is good underlying physics. So let us discuss this systematically. Let us first consider density less than 4.3 times 10 to the power 11 grams per cubic centimeter, which is the outer crust, which is 1 kilometer thick. How do you know all the things I said about those exotic nuclei, strontium, krypton, and other things are true? Well, I think you ought to believe it because that has been deduced by physicists based on very sound calculations. What are these calculations and what are the underlying principles? The problem of determining the equilibrium nucleus at any density, I have a certain density and I give you a certain number of protons and neutrons. How you pack them as nuclei is determined by minimizing the total energy per unit volume at a fixed density subject to charge neutrality. Of course, charge neutrality has to be maintained. So at every density, you have to calculate what is the thermodynamically most favorable packaging of neutrons and protons into atomic nuclei. And what is the principle that you will use? The principle that you will use is to minimize this energy. This energy consists of the energy of the nuclei. This is the energy of a nucleus whose atomic number is A and whose atomic charge is Z. The number density of the nucleus, the number of nuclei per unit volume, is this N subscript capital N. And then, of course, there are electrons whose number density is N subscript E. The electrons have energy. They have kinetic energy. They have interaction potential energy, Coulomb interaction between electrons. You have to add all these energies and then minimize this energy at a fixed density demanding charge neutrality. How do you calculate the energy of a nucleus of atomic mass A and atomic charge Z? You use something known as semi-empirical mass formula, which was first discovered by Carl von Weizsäcker in the late 1930s. We shall not go into that, but those of you who are studying MSc Physics would have studied this. The essence of this mass formula is simply the following. I form a droplet of liquid, droplet of water or a droplet of mercury. Then I ask, what is the optimum size of this droplet? How do you do that? There is a surface you have created by forming a droplet. There is a surface energy which gives rise to surface tension. There is also a volume energy. You have to add the two and minimize it, and that will tell you for each material what is the optimum size of a droplet. You use the same principle here using the semi-empirical mass formula. There are two energies. Niels Bohr taught us in the 1930s that the nuclei can be regarded essentially like a liquid droplet. This is known as the liquid drop model of the nucleus. So, given a packaging of neutrons and protons of a certain size and a certain charge, which is decided by the number of protons, I can calculate what is the surface energy of this nucleus, and I can calculate what is the volume energy of the nucleus. Then I have to add the two and minimize that. Fine. Now, I'm not going into the details. If you look at nuclear physics book, you can see that the nuclear surface energy is proportional to 1 over a to the power 1 by 3. Therefore, larger the value of a, smaller is the surface energy because this comes in the denominator. So the surface energy likes large nuclei. The surface tension will be smaller. On the other hand, if you take a large nucleus, there will be lots of protons and therefore lots of Coulomb repulsion. Therefore, from the point of view of minimizing Coulomb repulsive energy, the nucleus would prefer small nuclei. And the volume energy is proportional to a to the power 2 by 3 multiplied by z over a whole square per nucleon. So you see here a comes in the denominator. Here a comes in the numerator. Z over a for most nucleus is half, so that is 1 by 4. So essentially you're comparing a to the power minus 1 by 3 with a to the power 2 by 3. So proton repulsion, repulsive energy favors small nuclei, surface tension prefers large nuclei. So you have to combine this. So the balance between the surface energy and the volume energy will determine what is the optimum value of the total number of neutrons and protons inside the nucleus. So that is the principle that has been used below the neutron drift. Now, there have been some sophistications that have been added to this from the 1940s. In 1958, Harrison and John Wheeler said, how do we go to increasing Z and increasing A? They said, well, let's regard A and Z as continuous numbers. A and Z are not continuous numbers, it's either 1 or 2 or 3 or 4. But they said, when you go to large numbers, you can regard them as continuous variables. It's an approximation, but it's a pretty decent approximation in order to make some progress. Then somebody came and said, well, you have to remember that the nuclei have shell structures and there is energy associated with packing them in different shells. All right, you take that also into account. These are refinements. Then Bain, Pethick and Sutherland said, but look, you have forgotten lattice energy. You're only talking about nuclei, energy of the nuclei, competition between surface energy and volume energy. But you have arranged them as a periodic lattice. A lattice has a cohesive energy. There is lattice energy. If a piece of solid did not have cohesive energy, it will break up into individual atoms. So you have to add that energy also. Now that lattice energy, if you look in any elementary book on solid-state physics, like Kittel's book, is related to z squared E squared over the lattice spacing A. Therefore, the lattice energy, which is attractive, otherwise the lattice wouldn't be stable, reduces the Coulomb nuclear energy. So previously it was a competition between surface energy and repulsive Coulomb energy. Now the repulsive Coulomb energy has been reduced a little bit because I am adding to it a negative number, which is the lattice energy. So that helps to the level of 15% or so. So let me stress, these are refinements that were added over 20, 30 years. And detailed calculations were done of the equation of state, dependence of pressure on density. This is a plot of logarithm of the pressure on the y-axis against the logarithm of the density increasing along the x-axis. And I'm not going to tell you all these details. All I want to tell you is that different curves correspond to different approximations that you have made. But you'll say, well, they all look more or less the same. Well, they don't look more or less the same because this is a log-log plot. So, for example, that difference between the two equations of state is enormous. It's a log-log plot, so it's enormous. Now, let us go to a density greater than the neutron density. We come to a region where the neutrons are dripping out of the nucleus, that is in this density range. Then Boehm, Pettit, and Boehm, Hans Bethe, the great Hans Bethe and Pettit said, but look, there is a neutron fluid now. These neutrons and neutrons interact with each other by many body effects, just as electrons in a metal interact with other electrons, producing many body effects like ferromagnetism, superconductivity, etc. Similarly, he says that you must take into account the interaction energy between neutrons. Then, fine, take that into account. So that took 10, 15 years to incorporate. Then you say, let's go to a density greater than the nuclear density and come to the core neutron, proton, fluid core, the liquid interior. How do you calculate the energy in the liquid interior? You calculate that energy the same way as you calculate the energy of the nucleus. You calculate the energy of the nucleus by scattering experiments, shooting one nuclei against the other, and deriving the internuclear potential energy V as a function of R. And that tells you how to calculate the energy. You do the same thing. And then you have to solve the many-body Schrödinger equation because this is a quantum problem. And then Hans Bethe said around 1964-65, it is not enough to just take two body forces into account, but you must take into account three body forces and even four body forces into account. These are all incredibly sophisticated refinements that you need not be bothered with. All I'm saying is that people spend 30, 40 years refining this picture that I showed you. So that is the end result of very hard calculation by extremely knowledgeable and clever physicists over a period of more than 30 years. So here is the equation of drip, equation above the neutron drip, and all that calculation as what resulted in this picture, which is the outer crust is roughly 1 kilometer in thickness. It is a ferromagnetic iron lattice above a density of 4.3 times 10 to the power 11 grams per cubic centimeter. There is neutronization of matter, like Landau had said in 1938. That is the density where neutronization begins. Electrons disappear, protons disappear, and neutrons appear in place. And then what you have here is a lattice of exotic nuclei immersed in a fluid of neutrons. And then above the nuclear density, you have a liquid core consisting of 95% protons and 95% neutrons, and 5% protons. Fine. Now, I'm going to tell you something about yet another property of this liquid core. And it's a very exotic property. It concerns superfluidity and superconductivity in neutron stars. Now you will say, those of you who have studied something about superconductivity and superfluidity and say, look, this is all utter nonsense. I know that superfluidity and superconductivity are extremely low temperature phenomena. You have to have liquid helium temperatures below 2 degrees or even millikelvin. You're talking about a star whose temperature is 10 to the power 9 Kelvin. What nonsense is this talking about superfluidity and superconductivity? I'm going to convince you that it is not nonsense. It makes eminent sense to talk about it. First, let us briefly recall, for those of you who have not studied these phenomena, what superconductivity and superfluidity are. In 1908, the Dutch physicist Kamerlingh Onnes liquefied helium. It was a great technical achievement. Helium nuclei have such low mass that it was very difficult to liquefy it. Oxygen had been liquefied, nitrogen had been liquefied, air had been liquefied, of course, but liquid helium was finally liquefied by Kamerlingh Onnes. Within 3 years, in 1911, he discovered that at a temperature of 4.2 Kelvin, the electrical resistance of mercury became zero. Not small, but identically zero. And it became a superconductor. In other words, if I set up a current in the loop, the current will not dissipate in the age of the universe. In 1933, a German physicist, Meissner, discovered that a superconductor is a perfect diamagnet. In other words, if this is a piece of metal, let us say tin or mercury, and let us say it is permeated by a uniform magnetic field. I cool this metal below its transition temperature and it becomes a superconductor, then it expels all the magnetic field. In other words, it's a perfect diamagnet. So here is the proof that it's a perfect diamagnet. Here is a magnet in a bucket of superfluid helium. You need that low temperature for this to be a superconductor. And here is a magnet, the kind of magnet you stick on refrigerator doors. And you notice that it is levitating. That is because the superconductor does not allow the magnetic field to come near it. It repels the magnetic field, which is the characteristic of a diamagnet. So superconductors have many exotic properties. These are just a couple of them. In 1938, Kapitsa, the great Russian physicist, working with Lord Rutherford in the Cavendish Laboratory in Cambridge, discovered that at a temperature of 2.19 Kelvin, liquid helium-4 became a superfluid. Its viscosity became zero, identically zero. Now, a superfluid has several most remarkable properties. For example, if I have a superfluid in this bucket, this rectangular cubical bucket, and if I stick a test tube like that, then the superfluid will climb along the walls of this test tube and flow into this test tube. The test tube will get filled with superfluid, although I have not dunked the test tube inside the superfluid. Similarly, if I have a superfluid in a little bowl and I hang it, then the superfluid will climb over the rim of the bowl and drip down. Or if I have a superfluid inside a flask like this, it will come out as a fountain. This is known as a fountain effect. These are all exotic phenomena not exhibited by ordinary liquid. These are properties of a superfluid whose viscosity is zero, just as the electrical resistance of a superconductor is zero. both these are ultra low temperature phenomena. Now, the great Russian physicist Landau, whose name we have encountered many times already, constructed a successful theory to explain superfluidity, for which he was awarded a Nobel Prize in 1962. Much later, in 1978, the Nobel Committee thought it was an oversight not to have given Kapitsa a Nobel Prize. So eventually he was awarded the Nobel Prize for his pioneering and insightful contributions to low-temperature physics, including the discovery of the phenomena of superfluidity itself. Now, in 1938, Fritz London argued that both superfluidity and superconductivity are related to the phenomena known as Bose-Einstein condensation. This phenomena was finally experimentally demonstrated a few years ago, and the Nobel Prize for Physics was awarded for this experimental demonstration of Bose-Einstein condensation. Now, I have no time to explain to you what this Bose-Einstein condensation is, but briefly it is the following. You know that both according to Maxwell-Boltzmann statistics and according to Fermi-Dirac statistics, given a certain temperature, there are rules that tells you how to populate the various energy levels. In the case of Boltzmann distribution, it's an exponential distribution, e to the power minus e over kt. In the case of Fermi-Dirac distribution, you know what this distribution function is. Now, if the particle obeyed Bose-Einstein statistics, like pi mesons or helium-4 nuclei and so on, then what Einstein discovered in 1922, although the name Bose-Einstein condensation is used, it was really Einstein's discovery, and Bose did not play any role in this discovery. Einstein showed that at low enough temperature, all the particles will be in the E equal to 0 state. That is the phenomena of Bose-Einstein condensation. All the particles will be in the zero momentum state or zero energy state, which is not allowed in Maxwell-Boltzmann statistics or in Fermi-Dirac statistics at finite temperature. But you're allowed to do that with Bose-Einstein particles as long as you are at a temperature below. So what Fritz London argued was both superconductivity and superfluidity are in some way related to the phenomena of Bose-Einstein condensation. In 1957, Bordeen, Cooper, and his student Schrieffer developed the mathematical theory of superconductivity, for which they were awarded the Nobel Prize for Physics. And that theory says that electrons, as you know, individually obey Fermi-Dirac statistics and Pauli's exclusion principle. So they cannot all be in the zero momentum or zero energy state. So they cannot undergo the phenomena of Bose-Einstein condensation. But they can if I can convert two protons into a boson. In other words, if I put a rubber band around two electrons and make them behave like a Bose-Einstein particle, then under suitable circumstances, I can make those two electrons with the rubber band around them all sit in the zero energy or zero momentum state. But you'll say that's not possible. Two electrons repel each other. You cannot bring them close together and bind them. Well, that is why they were awarded the Nobel Prize. They showed that, yes, two electrons repel each other according to Coulomb repulsion, but they can also attract each other by exchanging a lattice vibration. That is in the quantum picture. They exchange what is known as phonons. Phonons are quantized lattice waves. Lattice sound waves, if you like. And the way that happens is the following. An electron is going by, and these are the nuclei, and because there is a negative charge, these positive charges come closer together, so there is an excess positive charge over there. This electron has gone off, and then some other electron, so this is the idea of a retarded attractive potential. Electrons at the Fermi surface level travel with a velocity which is the Fermi velocity, which is the Fermi momentum divided by the mass of the electron. As they pass through the lattice, the positive ions respond slowly over there. For example, the positive ions respond slowly. By the time they have reached their maximum excursion, which is shown over here, the four positive charges have come closer together than in a normal lattice. The electron is gone. But it leaves behind a region of excess positive charge. And some other electron, a second electron, is attracted to this. So it's a retarded potential, if you like we discussed in electromagnetism. So the interaction between two electrons mediated by lattice vibrations leads to a net attractive interaction between two electrons. And these two electrons of opposite spin bind one another. This is a rubber band in momentum space. Physically, these two electrons are not near one another. They are far away. But there is a rubber band around them in momentum space. Now, these particles, which are known as Cooper pairs, two electrons with opposite spin on the Fermi, diametrically opposite points on the Fermi sphere, behave like bosons, and they go into a zero energy or zero momentum state, and that's what gives rise to the phenomena of superconductivity. Well, if you understood something about it, is fine. If not, don't bother. Let's go ahead. So, for those of you who understood a little bit, here is a quick summary. Cooper pairs are bosons. Superconducting state is a bosonic condensate. It is a coherent state, like photons in a laser or a maser. It's a macroscopic quantum state. So if I have a bucket of superfluid, or if I have a large chunk of a superconducting metal, it's a quantum state just as an atom or a molecule is a quantum state. A superconductor is not just a metal with zero resistance. It has different thermodynamic properties. It is a diamagnet. Now, the difference between a normal metal and a superconductor is a very small energy difference. It's only a few milli-electron volt. An electron volt is 10,000 degrees. A milli-electron volt is about 10 Kelvin. That is why superconductivity is a low temperature phenomenon. Now I'm talking about superconductivity at a temperature of 10 to the power 9 Kelvin. Now you'll say, but that's ridiculous. Well, not so ridiculous. Bardeen, Cooper, and Schrieffer constructed the theory of superconductivity in 1957. As soon as the news of the BCS theory reached Moscow, Landau's young associates and students used BCS theory to make compelling arguments that neutrons in the core of a superfluid, neutrons in the core of a neutron star will be superfluid. That was said by Ginsburg in 1960. Migdal, 1 year earlier, said the protons in the core of a neutron star will be superconducting. But the electrons will be normal because they are light and still moving fast. Now, you need an attractive force between two protons and two neutrons to make them a superconductor or a superfluid. In the case of electrons and metals, you have to go through this lattice mediation and so on. Here, you don't have to do anything. The force between two neutrons, the force between two protons is naturally attractive and incredibly strong. This is the strong nuclear force. Therefore, they will form Cooper pairs. And as long as the temperature of the star is below the calculated transition temperature, they will become superconducting. They will become superfluid. Now, Bardeen-Cooper-Schrieffer theory tells you that the transition temperature is proportional to exponential to the power 1 over the density of states at the Fermi level and the attractive potential. The density of states is just the number of states between EF and EF plus or minus dE. In a small energy interval, dE around the Fermi energy, how many states are there? V is the attractive potential, N is the density of states. Now, Migdal and Ginsburg estimated that the transition temperature to superfluidity and superconductivity is of the order of 10 to the power 10 Kelvin. But the star is only at a temperature of 10 to the power 8 Kelvin or so. Therefore, the temperature of the star is well below the transition temperature. The transition temperature between a paramagnet and a ferromagnet, which is known as the Curie temperature, is around 700 degrees. Therefore, at 300 degrees, iron is ferromagnetic. So we are saying the same thing. The transition temperature from normal to superfluid or normal to superconductor is 10 to the power 10 Kelvin. The star is at a temperature of 10 to the power 8 or 10 to the power 9 Kelvin. Therefore, there is no question of doubting this at all. So let's skip all this. So I just want to show you that people have done honest to goodness calculations and convinced themselves repeatedly that the interior temperature of a neutron star is of the order of 10 to the power 8 Kelvin. The Fermi temperature is 10 to the power 12 Kelvin. The transition temperature to superfluidity and superconductivity is of the order of 10 to the power 10 Kelvin, and therefore the temperature of the star is much, much smaller than the transition temperature. Therefore, you should not doubt this statement. Now, there is an exotic twist, and I shall merely state that and end on that note. Now, the superfluid and superconductor are in a further exotic state. Let us first discuss the superfluid. Let us imagine a superfluid is in a bucket and I rotate the bucket. Normally, if the bucket is filled with water, what will happen? I rotate the bucket. Sooner or later, the water will also start rotating because the water rubs against the wall of the bucket, and then water rubs against water, and therefore sooner or later, the entire body of water is also rotating with the same angular velocity as the bucket itself. Now, if this bucket is filled with superfluid, it cannot do so. It cannot rotate. And the reason it cannot rotate, this is something that you have to accept because I do not have the time to develop this argument, is rotation means curl of the velocity is not zero. Curl means velocity. Look at Murray Spiegel's book on vectors in the Schwamm series. They'll give geometric interpretation for divergence and curl. Curl is rotation. So in order for a liquid to rotate, curl of the velocity should be non-zero. But quantum mechanics tells you that the curl of the velocity of a superfluid is zero. So a bucket of superfluid helium cannot rotate. And yet thermodynamics tells you that in order to minimize the free energy, it would be a lot better if it could rotate. Now, this problem remained unsolved for a long time. It was solved by the great chemist Lars Onsager in 1949, and several years later, independently, by the great Richard Feynman. What they basically said was the following. Yes, it is true that the superfluid cannot rotate. So what it does very cleverly is creates regions inside the superfluid where it destroys superfluidity. And because in that region, it is not a superfluid, but it's a normal fluid, you can have rotation. So what you have here is shown, all these dots are, the bucket is going into that slide. All these dots are needle-like structures in the fluid where superfluidity has been destroyed and where there is a little circulation. So you have an array of vortices. Now the core of the vortex is normal. Now this vortex is not like a vortex in your wash basin or in your cup of tea. You're dealing with a quantum liquid. A superfluid is a quantum liquid. So just as in an atom, angular momentum cannot have any values. It must be multiples of Planck's constant, 1h or 2h or 3h. Similarly, this circulation cannot also have any arbitrary value. It must be in multiples of the quantum of circulation, which is Planck's constant divided by 2m. Convince yourself dimensionally, Planck's constant divided by mass as the dimension of circulation. So what you have is a large number of quantized vortices. Each quantized vortex having a circulation of 5 which is equal to h divided by 2m. So if I have a rotating bucket, then what the fluid does is to create n vortices, capital N vortices, each with the circulation given by quantum mechanics, which is Planck's constant divided by 2m. Therefore, this total circulation is the circulation the fluid would have if it rotated macroscopically as a rigid body. It is not allowed to rotate rigidly as a body, therefore it creates these vortices. But the sum of the quantum of circulation of all these vortices correspond to this. Now, in a neutron star spinning with a period of 1 second, once every second it rotates, you can estimate that there are roughly 10 to the power 16 quantized vortices, as argued by Lars Onsager in 1949, and by Feynman in 1956. Now you will say this is all science fiction. I don't think so, because recently Bose-Einstein condensation has been achieved by trapping atoms in crossed laser light. And as you rotate these droplets, you see these quantized vortices appearing, and the number of vortices increases as you spin the droplets faster and faster and faster, exactly as Feynman and Onsager, or Onsager and Feynman had said long time ago. So here is another spectacular picture of experimental proof of quantized vortices. Now, you may say, this is all amusing, but what has this got to do with pulsars and neutron stars, and what has this got to do with astrophysics? Well, a lot of things. If superfluidity occurs, then it has many important astrophysical consequences. For example, it is known observationally that there are star quakes in neutron stars. Suddenly they spin up, and then they relax back to the original spin. Now, these star quakes are very much stronger than earthquakes. The earthquake on Earth, seismic activity on Earth, is measured in Richter scale. And if you have an earthquake of 7 or 8, then it's a massive earthquake. It causes tsunamis. It's a logarithmic scale. A star quake in a neutron star will be 50 on the Richter scale. Please remember, I'm talking about a logarithmic scale of energy. So these star quakes in neutron stars are incredibly powerful events. The recovery after the star quakes is very slow indeed. And that can only be explained if the interior is a superfluid. And people have conjectured that quantized vortices may also be responsible for the expulsion of magnetic fields from neutron stars. This is a subject that we shall come to later on when we discuss the millisecond pulsars. Now, before I conclude, I would like to say that superconductors also behave in very exotic manner. I mean, they're already exotic, but this is an extra degree of exotic behavior. I already told you superconductors are diamagnets. Therefore, you would think that you cannot have a magnetic field inside a superconductor. It will expel. But that's not true. Alloys, all metallic alloys, when they become superconductor not like lead or tin or mercury. They become what are known as type 2 superconductor. Now, type 2 superconductors do allow, in a certain range of magnetic fields, do allow a magnetic field to penetrate through it. It doesn't expel the magnetic field. But the magnetic field can only penetrate the superconductor as quantized vortices. Now, this was first argued by Abrikosov, one of Landau's students, and he constructed a theory of type 2 superconductors and quantized vortices way back in 1958. But Landau did not allow him to publish the paper because he thought this was all nonsense. But long after Landau died, the paper was published, and in 2003, Abrikosov received the Nobel Prize for Physics for this extraordinary discovery. Now, what Abrikosov showed in the paper in 1958 is that type 2 superconductors will allow magnetic flux to penetrate through it as long as it does so as quantized flux tubes. Just as we had quantized vortices, you have quantized flux tube. Dimensionally, the quantum of flux is Planck's constant multiplied by the speed of light divided by 2 times the charge of the electron. So, if I have a magnetic field penetrating a type 2 superconductors, it will create the necessary number of these quantized flux tubes, and the flux will be confined to these things. You'll say, well, this is all fine, you might have got the Nobel Prize, but where is the proof of all these things? Well, there it is. Here are experimental photographs of quantized flux tubes in a type 2 superconductors. Just as I showed you quantized vortices in a droplet of superfluid Bose-Einstein condensate, here are quantized flux tubes in a superconductor. So what you have inside a neutron star are 2 brands of spaghettis. You have the magnetic vortices parallel to the magnetic axis, and you have the Feynman-Onsager quantized vortices parallel to the rotation axis. The yellow ones are the vortices, and the red ones are the flux tubes. Both are quantized. Well, let's conclude. This is the first instance that we know of where superconductivity and superfluidity coexist. On Earth, we have superfluids, we have superconductors, but we know of no situation where both the phenomena occur together. And in a neutron star interior, they do. And astronomers believe their interaction between these 2 superfluid states, namely the interaction between superfluidity and superconductivity, may be responsible for such phenomena as star quakes, flux expulsion from the interior, plate tectonics in neutron stars, and so on. Now, finally, we can ask the following question. Right at the center, I have put a question mark. What is happening at the center? Some people have conjectured that right near the center, you have pi mesons and k mesons. And at the very center, you will have quarks. Now, if pi mesons and k mesons do occur in a neutron star, then it will make the neutron star highly unstable against collapse, because k mesons and pi mesons obey Bose-Einstein statistics, and therefore they can condense into a state of zero momentum and therefore zero pressure. Therefore, the pressure that was supplied by the electron disappears and the pressure becomes zero. Therefore, the neutron star can collapse to a black hole. But so far, there is no evidence to suggest that pi mesons and k mesons do occur in the neutron star. Right at the very center of the neutron star, people have conjectured, just as when you press nuclei together, the nuclei melted into a sea of neutrons and protons. When you press 2 neutrons or 2 protons really into one another, then the 3 quarks which make up the neutrons and 3 quarks which make up the protons, they will spill out, and you will have just a soup of quarks. This at the moment is a conjecture. All we can say with some degree of confidence is this picture, which I shall repeat once again without further commentary. So that, my friends, is what we think the internal structure of the neutron star is most likely to be. And that's what you would find if you went on a journey to the center of the neutron star. Who knows, you may find there is a droplet of quarks in the center. But that is sheer speculation. In the next lecture, we shall discuss the maximum mass of neutron stars. Chandrasekhar showed that there is a maximum mass to a white dwarf. Similarly, one can ask, is there a maximum mass for a neutron star? This is an interesting question, and this is a prelude to the formation of black holes. Therefore, look forward to the next lecture. Thank you very much.